first thing that we're going to talk about today is intervals on which a function is increasing and decreasing. So we've talked a little bit about this already last time when we were graphing the derivative of a function given the graph of the original function. So we know already that if the derivative of a function is greater than 0 on some interval from a to b, then we would say that f is increasing on that interval. And if the derivative of a function is negative, less than 0 on some interval, then the function must decrease on that interval. Now, you probably first look at this and notice that there's a discrepancy here where this is an open interval and this is a closed interval. Normally, I would say that a function increases on only an open interval and decreases on only an open interval, because at the point where it stops increasing and starts decreasing, where we have a local min or a local max, the function is neither increasing nor decreasing. But for the AP test and for everything we do in this class, because I want to model what it says on the AP test, we have to include the endpoints of increasing and decreasing intervals, because the College Board says that we should use closed intervals for that. So anytime we're talking about an interval where something is increasing or decreasing, if the endpoint is a defined point on the function and it's continuous through that point, we will include that endpoint. So the only thing we have to do to figure out if a function, for example, a function f of x equals x squared, is increasing or decreasing on a specific interval is find its derivative. So we'll do that. And then we need to figure out when is the derivative positive and when is the derivative negative. Well, we've already talked about the only way for a function to have a local max or a local min is if its derivative is equal to 0 or if its derivative is undefined. So in this case, x equals 0 is a critical value, and we know that f prime is undefined at no values. That's never true. So we only have one critical value at x equals 0. And it is impossible for a function that is impossible for a function to change from increasing to decreasing somewhere that it doesn't have a minimum or a maximum. Or the only other possibility is if the function is not defined at some specific point, if there's a discontinuity. So we'll have to think about discontinuities of other functions, but this one doesn't have any discontinuities. So we know that the only place it changes from, it could possibly change from increasing to decreasing or vice versa, is at x equals 0. And so what we'll do is we'll make a sign chart, and I'm going to indicate that this is a sign chart for the derivative. And here's x equals 0 on my chart here. And any value less than 0 then should, when plugged into my derivative, either make the derivative positive or it should make it negative. And there's, every value to the left of 0 will either make it positive or it will make it negative. It's not that some values to the left will make it positive and some will make it negative, but they will all, in this case, make it negative, because if I plug a negative number into 2x, my derivative, I get a negative value. So my derivative is negative, which means that the function f must be decreasing. And then I want to check something on the other interval. Anything greater than 0 plugged into the derivative, 2x, will give you a positive value, which means that f must then be increasing. And we knew this to be true because we know what f of x equals x squared looks like. It's just a regular old parabola. So we knew that this function is increasing from 0 to infinity, and it is decreasing from negative infinity to 0. And you'll note that I included 0 with a bracket for both of those intervals, because that is a defined point on the function. But infinity will still be put into a parenthesis because it will always be in a parenthesis. Infinity is not a closed endpoint. So these are the intervals on which our function increases and decreases. And we'll go ahead and do the same thing here with f of x equals x cubed minus 4x. So the first step will be to take a derivative. F prime of x is equal to 3x squared minus 4. And if we were to set that equal to 0, we would end up with x squared equals 4/3, or x equals plus or minus 2 over root 3. We'd also want to note that f prime is never undefined. So there are no other critical values other than positive 2 over root 3 and negative 2 over root 3. So I'll make a sign chart that includes negative 2 over root 3 and positive 2 over root 3. Those being the only two places where the sign of that function, 3x squared minus 4, could possibly change. If we plug in something like 0 into the derivative, and I'm thinking 0 because it's between negative 2 root 3 and positive 2 over root 3, and it's a really easy number to plug into my derivative. If I plug in 0, I get negative 4, which means that this function must be decreasing on that interval. If I plug in something more than 2 over root 3, my derivative there, something like, let's say, 1,000,000. 1,000,000 squared times 3 is a pretty darn big number, and if I subtract 4, I end up with a positive value. So our function f must be increasing. And again, if I plug in something less than negative 2 over root 3, like negative 1,000,000 or negative 5, and then I square it and multiply it by 3, I'm going to get a positive value that's more than 4. And when I subtract 4, it'll stay positive. My derivative will be positive, and the function will be increasing. So now we can see that this particular function is increasing from negative infinity to negative 2 over root 3. And then, again, from 2 over root 3 to infinity. And it must be decreasing on the interval between there, which is negative 2 over root 3 to 2 over root 3. And even though it seems counterintuitive, we're going to include the endpoints in brackets other than the ones at infinity, even though that's telling us that our function is both increasing and decreasing at negative 2 over root 3 and positive 2 over root 3. So we're going to add just a little bit to this, which is something we've also still talked about. And the first thing is that if f prime changes from positive to negative at some value c, then that gives us a local maximum. And if f prime changes from negative to positive at c, that gives us a local minimum. So if we look back real quickly to the previous problem, we could see from our sign chart that we went from increasing to decreasing and decreasing to increasing. Therefore, we must have had a local maximum at negative 2 over root 3 and a local minimum at 2 over root 3. If there isn't a sign change when you investigate it on your sign chart at that value of c, at your critical value, then there is no local extrema at c. So that's very important. And what we've got done here is what we talked about the last time, where endpoints can be local minima or maxima as well. So if we have a left endpoint, as long as the function increases past it, we have a local minimum. So if we have a left endpoint and the function is increasing, then this is a local minimum. If we have a left endpoint, the function decreases, we have a local max. And likewise down here at a right endpoint, if the function is decreasing into that endpoint, we have a local minimum. And at a right endpoint, if the function increases into that, we have a local max. So we're going to use that to now figure out all of the local extrema for x cubed minus 12x minus 5. So the first step will be to find f prime of x, which is 3x squared minus 12. We'll set that equal to 0, and we'll see when it's undefined. And obviously, it's not ever undefined. And that's not always going to be the case, but more often than not, the derivative will be defined for all values. And when we're looking at polynomials, it certainly will be. But when we factor out the 3, and then continue to factor, using a difference of squares, we end up with x equaling negative 2 and x equaling 2. I'm not sure why I wrote a 3 there, but x equaling 2 as our only two critical values. And so we'll put those two critical values onto a sign chart. And we will evaluate some number on each interval. So between negative 2 and 2 would be something like 0. If I plug 0 in, a 3 is positive, 0 plus 2 is positive, and 0 minus 2 is negative. A positive times a positive times a negative yields a negative, which tells us that on this interval, our function decreases. If we evaluate f prime of something greater than 2, like, I don't know, 735, doesn't really matter. Any value greater than 2 will do. The 3 is positive. The x value we've chosen plus 2 is positive, and the x value we've chosen minus 2 is also positive. And now our function is increasing because a positive times a positive times a positive is a positive. And lastly, if we pick something less than negative 2, like f of negative, whatever number I just wrote there, looks like negative 1,000,000. The 3 is still positive. It's f prime of that number. The 3 is positive. That x value plus 2 is negative, and that x value minus 2 is also negative, giving us a positive times a negative, which is positive, and our function must increase. Therefore, we can see that because our derivative is going from positive to negative, negative 2, this is where we have a maximum, and here we're going to have a local minimum. And it asks us, what are the local extreme values? So we'll investigate what f of 2 is. That'd be 2 cubed, which is 8, minus 12 times 2, which is 24, minus 5. 8 minus 24 is negative 16, minus 5 more is negative 21. And when we find f of negative 2, that'll be negative 8 plus 24 minus 5, and that'll give us 16 minus 5, or 11. And so it looks like we have a local max of 11 at x equals negative 2, and a local min of negative 21 at x equals positive 2. And then the question also asks us to identify if any of these are absolute extrema. And so we have to then think about the end behavior of our function. And this is the cubic. And so nothing weird is really happening with the cubic. We know that as it goes towards infinity, when a is a positive 1, we go towards infinity, this is going up towards infinity. And as I go towards negative infinity, it's going down towards negative infinity. Therefore, we are not going to be having any absolute extrema because our function goes down to negative infinity and up to positive. So we'll just write over here, no absolute extreme. Now we're going to look at a function that's maybe not quite as familiar. X squared minus 3 times e to the x. And we're going to then try to find local extrema and see if any of them are absolute extremes. So our first step, again, is going to just be to take a first derivative, which this time we'll have to use the product rule. That'll be x squared minus 3 times the derivative of e to the x, which is e to the x, plus the derivative of x squared minus 3, which is 2x, times e to the x. And in order to see when this is equal to 0, we'll want to factor out an e to the x, leaving us with an x squared, a plus 2x, and a minus 3, at which point we can continue factoring. That turns out to be x plus 3 and x minus 1. And that gives us a critical value of x equals negative 3, x equals positive 1, and e to the x equals 0. Well, that has no solution. If we tried to solve that, we'd have to take the natural log of both sides. And you can't take the natural log of 0, so we get no critical values from that. We should also check and see when is f prime undefined. But the answer to that, again, is never, because I can take any number and square it. I can take any number and multiply it by 2. I can take the sum of those two numbers and subtract 3, which is just some number. And if I take that number, I can multiply it by e to the power of any number. So f prime is never undefined. So now our sign chart will just include negative 3 and 1. And if we choose something less than negative 3, like negative 1,000,000, and plug it into our derivative, e to the negative 1,000,000 just means 1 over e to the 1,000,000 power, which is a positive number. And x plus 3, well, that's negative 1,000,000 plus 3, that's a negative. And negative 1,000,000 minus 1 is a negative, which means we end up with a positive, which means our function increases. An easy number between negative 3 and 1 to plug in would be 0. E to the 0 is a positive 1. 0 plus 3 is positive, and 0 minus 1 is negative. A positive times a negative gives you a negative, and the function decreases. And then something greater than 1, like 1,000,000, makes all three of these pieces of our derivative positive, telling us our function starts increasing again. So we should have a local max at x equals negative 3 and a local min at x equals 1. Now it becomes really important for us to really check what's going on with the end behavior here. Since this isn't just a cubic that we know goes to infinity and negative infinity on each side, we really need to investigate the limit as we approach infinity and negative infinity. So if I were to look for a limit as x approaches infinity of f of x, well, that's just going to be infinity squared minus 3, which is infinity, times e to the infinity, which is also infinity. Infinity times infinity is infinity. So this is going up towards infinity. But if I looked at a limit as x approaches negative infinity of f of x, we have negative infinity squared minus 3, which is infinity, times e to the negative infinity. Okay? And this is effectively an infinity squared here. And if I have e to the negative infinity, that's like 1 over e to the infinity. And we know that e to the infinity increases more rapidly than infinity squared. If infinity isn't really infinity, it's just some large x value. This denominator is going to get larger much more quickly than the numerator, which means this is 0, which means this is actually going down, but always staying above 0. So we need to keep that in mind when we're thinking about absolute minima. We know we're not going to have any absolute maxima because on the right it goes to infinity. So when we plug in -3 and we plug in 1, and let's do that here, f of -3, -3 squared is 9, minus 3 is 6. And we have 6e to the -3. And then f of 1 is 1 squared, which is 1, minus 3, which is -2, times e to the first is just e. And so we can see that as we follow along the trajectory of this graph, we're going to get to a value of -2e, which is a local minimum. But if over here on the left we were staying above 0, it would tell us that this graph must kind of follow a trajectory that looks like this. We are going towards 0. We're increasing to a local max. I kind of threw this over a little further than I should have, maybe. See if we can drag that over a bit. It's going to look more like that. Let's say this is at -3 and this is at 1. We're going to have an asymptote here at 0. We're going to go up to our local max, down to a local and absolute min, and then increase to infinity. So we would say we have a local max of 6e to the -3 at x equals -3. And we have a local and absolute min of -2e at x equals 1. The next quick thing that we're going to talk about here today is concavity. And we've talked quite a bit about what concavity is. So it's important for us to remember that a function that is concave up looks like this, and a function that is concave down looks like that. And if our derivative increases, that means its derivative must be positive. And a derivative increasing means that the slopes are increasing, and that is the exact definition of being concave up. And if these slopes are decreasing, that is the exact definition of being concave down. Our slopes are decreasing across that domain. So we're going to start looking for when a second derivative is positive and a second derivative is negative to determine if a function is concave up or concave down. So we'll start with a real easy one. F of x equals x squared. We'll look for the second derivative. So f prime of x is 2x, and f double prime of x is just 2. Well, if our second derivative is positive, then that means that this function must always be concave up. And we should have known that to be true because we know what x squared looks like. It's just a concave up parabola. But if there was a possibility of the second derivative changing signs, i.e. the second derivative was equal to 0 or was undefined at some specific x value, we'd need to make a sign chart with our second derivative. So we'll see that right here with 2 plus sine x on the interval from 0 to 2 pi. So step 1 to determine the concavity is take a derivative. F prime of x is, well, the derivative of 2 is 0, and the derivative of sine is cosine. And then a second derivative, f double prime of x is just negative sine x. F double prime of x equals 0 whenever sine of x equals 0 on this interval. Well, the only place where sine of x is going to equal 0 between 0 and 2 pi would be at x equals pi. So we don't need to include anything else anything other than pi on our sign chart here, because f double prime is never undefined. You can take the sign of any number. So we'll now make a sign chart with our second derivative. And I'm going to put pi in the middle. And I will be careful because I have a restricted interval here of 0 and 2 pi to not test anything outside of those intervals, because that may end up messing up the values that I get. So if I plug in, let's say pi over 2 to my second derivative, that's negative sine of pi over 2. And the sine of pi over 2 is 1, so this is negative 1, which makes this whole interval negative, which means we are concave down on that interval. And if I pick something between pi and 2 pi, like let's say 3 pi over 2, the sine of 3 pi over 2 is negative 1, and the opposite of negative 1 is 1. Therefore, we're positive, and we are concave up on this interval. And the College Board gets it right this time. Intervals of concavity will 100% of the time always be written using parentheses, open intervals. So this is concave up from pi to 2 pi, and it is concave down from 0 to pi. So right in line with us talking about concavity is finding points of inflection. As we've talked about a bit this year already, a point of inflection is a place where a function has a tangent line, where its tangent line exists, so the function exists there, but the concavity changes. And so we'll, just like for the last problem, make a sign chart, and then we'll go in and see if the concavity changes at any of the places where the second derivative was 0 or where the second derivative was undefined. So if we look quickly back at the other one, we could have said that there must be a point of inflection at x equals pi, because that's where our concavity changed. So we'll take this function, f of x equals e to the negative x squared. We'll take its derivative, which is e to the u, so e to the negative x squared, times the derivative of negative x squared, which is negative 2x. And then in order to find the second derivative, we'll use the product rule. E to the negative x squared times the derivative of negative 2x, plus the derivative of e to the negative x squared, which is e to the negative x squared times negative 2x, times negative 2x. And so factoring out the e to the negative x squared from this gives us negative 2 plus negative 2x times negative 2x, which is 4x squared. And if we set this equal to 0 and look for when it's undefined, and I'll write the undefined part over here. When is this undefined? The answer again is never, because you could square any number, multiply that by 4 and subtract 2 from it, and you can take e and raise it to any number, and you can take any number and find negative x squared for it. So it's never undefined, but it does equal 0 when the piece in the middle here equals 0. So let's factor out the 2 from that, which will give us 2e to the negative x squared times 2x squared minus 1 is equal to 0. And e to the negative x squared will never be 0, but 2x squared minus 1 will be when x squared equals a half, or x equals plus or minus 1 over root 2. So we'll make a sign chart for a second derivative here with negative 1 over root 2 and positive 1 over root 2 on it. And an easy number between those to plug into our second derivative would be 0. So I'm going to put this up here at the top. F double prime of 0. Well, if I plug that in, 2 times e to the 0 is a positive number. And 0 squared times 2 is 0, minus 1 is a negative number. Positive times a negative gives us a negative, telling us this is concave down on that. And then we'll plug in something more than 1 over root 2, like, well, I don't know, 1,000,000. So f double prime of, I don't know, we'll just write 1,000. I don't feel like writing that many zeros. The first part of it, 2e to the negative x squared, is certainly always going to be positive. And then the second part, 1,000 squared times 2 minus 1 is also positive. And we'd see that if I did the same thing with, let's say, negative 1,000, e to the negative x squared is still always going to be positive. And when I square that negative value in the 2x squared minus 1, I'm still going to end up with a positive. So for both of these intervals, it's positive and it's concave up. And that tells us that we must have points of inflection at both negative 1 over root 2 and positive 1 over root 2. And we're going to evaluate the original function at both of those values. And I'm going to just do them both at the same time, which is perfectly fine here, because what am I doing to them both? I'm squaring them both. So they're both just going to become a half when I square them, because we saw forget x squared is a half. So this just becomes e to the negative 1/2. Or we prefer 1 over root e. So we have 2 points of inflection. The first is negative 1 over root 2, 1 over root e. And the second is positive 1 over root 2, 1 over root e. It's really important for us to remember, though, that just because the second derivative is 0 or undefined doesn't guarantee that there is or isn't an inflection point or a point of inflection. So if I were to find a second derivative here, I'd have to find the first derivative. F prime would be 4x cubed, and f double prime would be 12x squared. We note that the only place this could change signs would be at x equals 0. But we can't just say, oh, there is an inflection point there. We have to make the sign chart. Okay? If I plug in a positive number to 12x squared, I get a positive number, and it's concave up on that. But if I take a negative number and plug it in, 12x squared as well, I still get a positive. So we have to make sure we actually have the sign change before we can say that there is an inflection point. So in this case, there is no point of inflection, and we should know that because we know what the graph of x to the 4th is. And it's also important to remember to check for when the second derivative is undefined. So here we have f prime of x is 1/3 x to the negative 2/3. And f double prime of x equals negative 2/9 x to the negative 5/3, or negative 2 over 9x to the 5/3. And if you forget to check, or when the second derivative is undefined, you might look at this and say, ah, the second derivative is never 0. It couldn't possibly have a point of inflection. But that's not true. F double prime is undefined at x equals 0. And if we were to make a sign chart with x equals 0 and plug in a positive number to our second derivative, a positive number raised to the 5/3 power is still positive. And if you multiply that by 9, it's still positive. And if you take negative 2 and divide it by that number, you end up with a negative, which means we're concave down on the center. But if you take a negative number, when you raise a negative to the 5th power, it's still negative. And when you cube root that negative, it's still negative. And when I multiply it by 9, it's still negative. But when I take negative 2 and divide it by that negative, I get a positive. So it's very important to make sure you also look for when the second derivative is undefined when you're checking for points of inflection. And don't forget to always make the sign chart just to confirm that it does change sides. Don't just say a place where the second derivative is 0 undefined is guaranteed to be a point of inflection. So the last thing we're going to do today is we're going to talk about a second derivative test for local extrema. So we've already figured out a first derivative test for local extrema, and we're still going to use that to some degree. But the second derivative test is going to allow us to determine if that critical value is a max or a min without making the sign chart every time. And sometimes this method is going to be useful because sometimes it's really difficult to find the second derivative. Sometimes it's very easy to find the second derivative, and we want to use the second derivative test, but it might be really difficult to plug in your critical values into the original function. So if our derivative equals 0, we have a critical point there, and the second derivative is negative, then that tells us it must be a local maximum. And we can say that must be true because if the second derivative is negative, it must be concave down, giving us a local max at that critical value. And vice versa, if the first derivative is 0 at an x value or at c, and the second derivative is positive there, we must be concave up, yielding a local minimum. So we're going to take the first derivative, find the critical values, and then evaluate the second derivative at them to determine the concavity of the function, and that'll tell us if it's a local max or a local min. This doesn't always work, so it's important to remember that if your second derivative comes out to be 0 at that point, well, then there's not a local max or a local min there. Most likely there's going to be a point of inflection, but you'll still want to make your sign chart with your second derivative to confirm that. And this does not work if it's a place where the second derivative is undefined. And I actually meant to write that f prime of c is undefined, but it won't work if the second derivative is undefined either. But it definitely doesn't work if the first derivative is undefined. This only works when the first derivative is equal to 0. Does not work for places where the first derivative is undefined. So we're just going to do one of these, and it's actually a function we looked at earlier that we already found the extrema of, or to find. We're going to just now use the second derivative test to just see another method to do. So first off, f prime of x is 3x squared minus, so I wrote a 4 there, 3x squared minus 12. And if we set that equal to 0, I must have written 4 there because I was kind of already anticipating that when I solve 3x squared minus 12 is equal to 0, I get x squared equals 4, and x equals plus or minus 2. So we've got two places where our first derivative is 0. All we're going to have to do is plug those into a second derivative. Our second derivative is just 6x. So if I take 6x and I evaluate it at 2, I get 12. 12 is a positive number, which means that the function is concave up at that point, which means we have a local min at x equals 2. And if I plug in negative 2, we get negative 12, which is less than 0, telling us the function is concave down, telling us we have a local max at x equals negative 2. And if we want to find the actual local extrema, we've just got to go and we've got to plug those values of 2 and negative 2 back in. And we did this earlier, but I'll write it out again. F of 2 is just 2 cubed, which is 8, minus 24, which is negative 16, minus 5 is negative 21. So we have a local min of negative 21 at x equals 2. And we have a local max of f of negative 2, which was negative 8 plus 24, which was 16, minus 5, which was 11. So a local max of 11 at x equals negative 2. And that's going to be it for this time. The next lesson, we're going to talk about how to put together all this information to graph, without our graphing calculators, a very, very perfect depiction of pretty much any function we can think of.